Hello and welcome to the SwiftBird, or rather, welcome back. This is the second part of the third episode on the first topic in this series. Never mind. I'm Yakov, and today we'll be talking about lazy initialization, the auto-release pool, and the alternatives to reference counting. Hopefully, after that, I'll be able to leave memory management alone, and instead focus on something more practical. If you find this video helpful, please give it a thumbs up, subscribe to the channel, and consider sponsoring it at the links below. With that said, let's move on to the first topic of today, which is lazy initialization. In Swift, as in many other languages, when you want to create a new object, the runtime needs to do two things for you. First, it finds some unused bytes in memory. That step is called allocation. And second, it actually creates the object, so it can be used in your program. This second step is called initialization. The separation of these two steps opens a few opportunities to make memory use more efficient. The key technique for that is called lazy or deferred initialization. Swift, still being a modern language by today's standards, does quite a few tricks to optimize the initialization process, and lazy initialization plays an important role in it. Here's the key idea. Instead of creating the object directly, you provide instructions how to do that at runtime. These instructions look like a closure, and act as a recipe that's used only when needed. If your program doesn't need the object, it doesn't use this recipe, and no resources are wasted. In Swift codebases, you find this pattern used all across the place. For example, preparing data to be displayed may involve formatting dates. The date formatter object is a relatively heavy one in terms of initialization. So unless you actually have a date to format, it makes a lot of sense to declare the formatter lazy. Another scenario where lazy initialization can help is when your app implements some sort of a caching mechanism. In that case, you can defer initializing your networking stack until the user has requested something that doesn't exist in the local cache. There's a few things to keep in mind when using lazy initialization. First, lazy properties are always declared as variables. That's because their values are not retrieved until they're called for the first time, and constants do not allow that. It also means that at any point you can reassign a lazy variable with any other value. Second, computed properties cannot be declared lazy. Though in terms of deferred execution they act just like lazy properties, there's one crucial difference. Computed properties run from scratch every time you call them, while real lazy properties run only once, and then they keep the resulting value. Third, global symbols cannot be declared lazy too, but that's because they're already lazy by default. That makes a lot of sense, because if the app tried to initialize every static property at launch, this would introduce a hefty delay. With the last 2 points in mind, sometimes you're left with the dilemma what to use for declaring constants. The expressions look very similar, and in fact the difference gets important only in a handful of cases. In general, I use a static constant when I'll be using it more than once, and for single use I go with a computed variable. But again, the difference is really negligible in most scenarios. And one more thing to be aware of, lazily declared properties are not thread safe out of the box. If multiple threads attempt to access the property, the closure which emits it may be called more than once. That is lazy initialization, one of the easiest tricks to make your app appear faster. Now let's talk about a thing lots of developers have heard of, but never used in practice, the auto-release pool. As with many other memory management concepts, the auto-release pool emerged back in the days of Objective-C, and even before automatic reference counting arrived. But it survived the ARC transition and even made it to Swift. The auto-release pool is an interesting tool. In MRC, it offers some elements of automatic memory management. But in ARC, it lets you regain some manual control over memory that was taken away from you by ARC. In either mode, auto-release pools play an important role, and if you use Cocoa without them, you're leaking memory. As you know, before automatic reference counting, you had to send retain and release messages to each object. But in addition to these two, there's a third message, aptly called auto-release. What it does is, instead of deallocating the object immediately, it adds it to an auto-release pool, which is basically a scratchpad. It keeps the objects for a while, but when it's drained, as it's called in this whole pool concept, it sends a release message to each of the objects. Normally, the pool is drained at the end of every event loop cycle, so by sending auto-release instead of release, you extend the object's lifetime for a moment. But why would you want that? You see, it's quite common for methods to create and return objects which are only needed for a short time. The calling code gets the result, processes it in some way, and then discards. Without the auto-release pool, it would be the calling method's responsibility to dispose of the created objects. But it may not have enough information to decide whether it's safe to release them. By sending the auto-release message, the called method clearly indicates that it wants nothing to do with the object after it's returned. And the auto-release pool handles the cleanup automatically. This technique is used in many built-in Cocoa APIs, such as NSString initializers and more. Moreover, Objective-C has an entire naming convention for that. The guidelines suggest how you should name your methods so it remains clear who's responsible for releasing the objects they produce. But I'm going too much into detail here. In ARC, including Swift, instead of an auto-release pool object, now you use an auto-release pool block. It looks like a closure, or block, as they're called in Objective-C and some other languages. To the developer, it acts like a box with one particularly useful feature. When the block ends, every object created within it receives a release message. In other words, you set explicit boundaries which limit the object's lifetime. In Cocoa and Objective-C, especially its pre-ARC variant, the importance of auto-release pools is quite significant, to the point where each thread must have at least one pool available, otherwise you'll be leaking memory. Adding objects to an auto-release pool was often used to group many short-lived objects together, or defer their deallocation, or do both. You see, releasing each object individually imposes some overhead, and in that scenario, draining the whole pool in bulk can be more efficient. In Swift, the auto-release pool is available for your convenience, but you don't really have to use it. One of the situations where it may come in handy is similar to the old use case. Imagine you've got a loop whose each iteration creates a new object. You don't need the object itself, just some part of it. Without an auto-release pool block, you'll be accumulating all the garbage until the entire loop finishes. But with this block, the objects are released at the end of each iteration. That's a pretty rare use case, but as always, the more tools you have at your disposal, the more flexible your code can be. I got one last topic for today, and this one is not about lazy pools. It's not even about automatic reference counting at all. Quite the opposite, it's about the alternatives to RC. I've already touched on the basics of manual memory management in a previous video, so I don't want to repeat myself. Besides, allocating and deallocating memory manually can't really rival reference counting in its ease of use. The main competitor to RC is garbage collection, and just as reference counting, it comes in multiple flavors. The most common one is called tracing garbage collection, and it uses the mark and sweep approach. This approach consists of two phases happening at regular intervals. During the mark phase, the garbage collector goes through the entire memory graph, starting from the program's root, and checks which objects are accessible. Those that are receive a flag. Then, during the sweep phase, all memory is scanned from start to finish, and objects which don't have the flag are considered garbage and cleared. The main downside of garbage collection is that it can introduce pauses to the program's execution. Instead of managing memory on an object-by-object basis, it freezes the entire program for a moment. No one enjoys glitches while scrolling or doing other stuff, and early iPhones weren't very powerful. But actually, early versions of Cocoa and macOS supported garbage collection as the alternative to manual memory management. The only alternative, as there was no automatic reference counting back then. Heck, Cocoa even supported coding in Java. Besides garbage collection, we've got something called region-based memory management. This technique is not very common, so I won't stop here for long. Basically, the program's memory is divided into multiple regions, each having an expiration date. When it arrives, the whole region is emptied. This approach works for programs whose objects have predictable lifetimes, but on iOS it's not really common. And then we have something quite unique. It is Rust with its ownership model. In Rust, each object in memory has an owner, and when that owner goes out of scope, the objects owned by it are destroyed. You can move a value to a different owner, or borrow it for a moment and then return. In Rust, these rules are enforced at build time, so when the program runs, the lifetime of each object is known beforehand. That makes the language extremely efficient, placing it right next to C with its fully manual memory management. By the way, in last year's update, Swift added similar tools for explicit lifetime management. So, to summarize, reference counting is not the only technique that exists to make memory management more approachable. Some of the alternatives may be even easier to use. But reference counting seems like the optimal choice for systems which heavily rely on real-time interactions, and at the same time have a limited amount of resources. In other words, systems like your smartphone or laptop. By now, I've covered many frequently asked questions about memory management in Swift. If you've got more, leave them in the comments, so I can do a follow-up video later. But my best interviews on either side of the table were never about remembering stuff. You may not know one specific fact, but if you're familiar with the big picture, you can make assumptions, think out loud, and often come to the right answer in the end. And even if it's completely wrong, your ability to analyze and reason usually earns you more points than an answer that you simply remembered. And that marks the end of this episode. This was the last video on memory management in Swift, at least for now. But I've got many more topics planned for this series. I just wish I had more time to work on them. You can help me by giving this video a thumbs up, subscribing to the channel, and supporting it at the links below. All of that is great motivation for me. I'll see you soon with a new video. Until then, make your references fly.